Welcome students. In today's class, we are going to solve the Poisson equation. So essentially, if you remember, Poisson equation, okay? So let's say that you have this equation, Laplacian of u equals to f, yeah, in omega. And what is omega? Of course, omega is assumed to be open and connected. Open and connected, okay, and minus Laplacian of u equals to f in omega. This is the problem which is called the Poisson equation, right? Now, how do we solve this problem? To do this, we are going to start with something called a fundamental solution. Yeah, we are going to solve the homogeneous problem. Let's see if we can do that. Yeah, so essentially, we are going to find something called a fundamental solution. Fundamental solution, okay. Now, so what is a fundamental solution? We will explain all of that, yeah, later. But for now, what we are going to do is we just, without thinking much, yeah, we want to solve this equation, Laplacian of u equals to 0. Clear? We want to solve this equation, and solving this equation, you can think of it right now as, we are solving it in omega, which is in Rn. Okay, let's just do that, yeah. Once we do that, then we will, from there we will go on, yeah, about solving the Poisson equation. So, how to solve this equation? See, in one of the problems in the assignment, if you can, figure it out, there is a problem where you are asked to show that the Laplace equation is invariant under translation. So, essentially, you see, Laplace equation, okay, is invariant under rotation. Obviously, it is invariant under translation, but it is invariant under rotation. What does that mean? It means that let's say, if you have a coordinate axis and if you rotate it, through some angle, whatever it is, yeah, let's say some angle theta, in the new coordinate axis, okay. So let's say u is defined here in the new coordinate axis. That's your v. Yeah. So this is the new coordinate axis after a rotation theta. It should not look like this. You do realize there is a change in theta angle, okay, but the point is this. So for that change, u may get changed to v, okay, but in this coordinate, let's say if Laplacian of u equals to 0, then in the new coordinate also Laplacian of, u is getting changed to v, right? Yeah, so Laplacian v will also be 0. So basically, if u is harmonic, v is also harmonic under a rotation. Okay, so since this is invariant, Laplace equation is invariant under rotation, what we can think of is we can look for, see, this problem, as you know, that there are many solutions for this problem, right? For example, if you take the coordinate axis, so u of x1, x2, xn, let's say you take any xi, any coordinate function, yes, then Laplacian u is equals to 0. Any linear function, so let's say x1 plus x2 plus xn, if you are taking, that will also solve this problem. Any constant will solve this problem, yeah, but we want something more fundamental, more, non-trivial, let's say, yeah. So how do you get it? So basically we are looking for, let's put it this way, we are looking for solutions which are radial. Clear? Which are radial. Why we are certainly looking for radial solutions? Because we know that Laplace equation is invariant under rotation. So if you rotate this u, yeah, the resulting function which you are going to get out of the new coordinates, that is also solves the Laplace equation, and hence, you can think of the solutions. The problem should admit radial solutions, right? Okay, radial solutions. If you do, what are radial solutions? I'm sure you guys know, but still let me just write it down. So by radial solution, we mean u of x must look like some v of r, okay, where r equals to mod x. Okay, so basically, see, radial solutions are those solutions. So essentially, u should look like, so basically, u of x should look like u of mod x. You understand? Okay. So essentially, for example, let's say ux equals to mod x if I'm taking mod x squared. Let's just take that. Yeah. So that's a simple problem. So u from where to where? This is from Rn to R. That's your u, right? Yeah. So do you think this is a radial function? Of course it is radial function, because u of x, you can write it like u of x and u of mod x are essentially same, right? I mean, so it's not u of mod x, it will be some function v of mod x. Okay. V of, so this is just abuse of notation. We should not write it like this. So it is basically u of x is v of mod x, some other function v of mod x. And what is v here? So where v of r, let's say, yeah, r is mod x I'm writing, v of r is r square, right? Yeah. And where so basically what it says is this function, yeah. So essentially what radial function, one of the properties of radial function is the following. So I'm not writing the following. So radial functions are, these are constants along del B, let's say 0R. Okay, this is one. So basically, if you think of, I mean, let's say radial functions in Rn, right? Yeah, you are taking radial functions of Rn. You take the point origin, and if you take the origin and think of a ball, the disk. Yeah, let's say in 2 dimensions, you think of the disk. You take the boundary of the disk. So basically, mod y x minus y is r. So this distance in r. If it is radial, then this function, this is basically the function has to take a constant value over this ball. Again, if you are taking another ball, it will take another value, but that will be constant. So basically, on this ball, let's say the value is 1. I'm just giving one example. On this ball is 1. Again, this ball it can be 2. But the thing is, over the ball, you take any point on the ball, it is always going to be same. Yeah, but when you change the ball, it of course changes. But you do understand what I'm trying to say. Okay, so on the boundary, yeah, so they are going to be constants. Okay, so let's find some solutions here, some functions. So essentially, what are we going to do? We are looking for u of x, which looks like v of r. Clear? V of r. Okay, and what is r? Where, as I have already mentioned, r equals to mod of x. So what is it? So this is x1 square plus x2 square plus xn square whole power half. Yeah, it's just a norm of x essentially. Yeah, and of course we choose v such that Laplacian of v, Laplacian u equals to 0, and v is such that Laplacian of u is 0. Okay, so essentially we are assuming that u is a solution of the Laplace equation, and since ux equals to vr, then we choose v such that this will happen. So if we do that, then so let's write this equation. Yeah, see, this equation is in terms of u. Let's write it in terms of v and see what happens. So if we do that, first of all, a little change of variable r with respect to xi. If we differentiate r with respect to xy, that will be half x1 square xn square to xi, right? So that will give you xi by all of these, yeah, all of these, sorry, this is minus half, yeah, that's a half is there, so half minus 1 is minus half times 2xi. So this is 1 by x1 square plus x2 square plus xn square whole power half, which is r. Clear? Okay, of course we are assuming that x non-zero. We are assuming that, yeah. Okay, so once we have this thing, there thus u xi. Okay, see here I have to find u xi, then they have to sum it up, right? What is Laplacian? If you remember, Laplacian of u is equals to summation u xi, right? So first of all, I find uxi and then again differentiate it and get uxi. So uxi, let's calculate that first. What is it? Yeah, this is chain rule. It is v prime of r xi, right? Which is xi by r. Clear? So that is there. Now and uxi xi is equals to v double prime of r, okay, xi square by r square plus v prime of r 1 by r minus xi square by r cube. Yeah. So how am I getting it? It's very easy. Yeah. You take this particular thing, you differentiate it. So let's just differentiate this one. So first of all, Leibniz rule. So basically, I differentiate this thing, leaving this thing aside. So when I differentiate this, it is v double prime of r, and then r xi, and then xi by r remains unchanged, right? So xi by r is there. V double prime of r and r xi. R xi is xi by r. So that is why v double prime of r xi square by r square. Clear? And again, I leave v prime of r here, and after that, differentiate this thing with respect to xi. So I mean, you do realize that first of all, it will be 1 by r. It is coming 1 by r. V prime is common, 1 by r. The differentiation of xi with respect to xi is 1. So this is why 1 by r minus. Again, you keep this thing and differentiate 1 by r. If you differentiate 1 by r, it is minus 1 by r square, and after that r xi xi by r. So this is minus xi square by r cube. Clear? Okay. So that is there. So this holds for I equals to 1 to n. This is for any I equals to 1 to n. I hope this is very clear here. This is just chain rule, nothing else. So by chain rule. Chain rule. Okay. Now, therefore, Laplacian of u is what? Laplacian of u is equals to v. See, this is this. You take the sum, that's Laplacian of u. So you take the sum from I equals to 1 to n. When you take this, what is happening? This is independent of r, I, this is independent of y. You are getting summation here. So that's r square by r square, that it becomes v double prime of r. Clear? Plus v prime of r. Let's see what happens here. If you take the sum 1 by r, if you take n sums, it is n by r minus. Again, if you take this thing, this is summation xi square is r square by r cube, which is 1 by r. Clear? So what happens here? If you just write it properly, it is v double prime of r plus n minus 1 by r v prime of r. Okay, and this is equals to 0. Yeah. Why? Because u is harmonic. See, if u is harmonic, Laplacian u equals to 0. Laplacian u is this. So essentially, this particular expression is 0. Clear? Okay. Now, if I want to say, let's say I want to find that explicit function, right? If I have to find the explicit function, I just have to solve this particular problem. Yeah. And do you really know how to solve it? Of course we know, because this is just a one variable function, right? This is so beautiful about this changing it to radial function. So here you see, this is just a function of one variable r. Clear? And now I know this is just an ODE which I know how to solve. So let's say if v prime is not 0, okay, then you can just solve this problem and you can get log of. I hope all of you guys can do. Solve this equation. Yeah, it's not very difficult to do. Okay, so the derivative of this thing. Yeah, this is equals to. I'm just writing it down. Yeah, I am not wasting my time on how to solve this thing. I'm absolutely certain all of you know this. Yeah, I'm just solving this problem. Yeah. So once I do this, I get this thing. So in terms of v prime, I get this, and for r positive, okay. So please solve this problem and you can get. So this is, you guys have to check it yourself. Yeah, I'm not doing this thing. This is very easy. Check it yourself. And for r positive, what do you get? You get v of r. What is v of r? It is essentially, this is in two parts. So a log r plus b. Okay. This is for n equals to 2. And you also get a by r power n minus 2 plus b. This is for n greater than equal 3. Okay. So for n equals to 2, you get a different expression. For n greater than equal 3, you get this expression where a and b are constants. Where a and b are constants. Okay. This is just your ODE, usual ODE. Yeah. Again, emphasize, please check. Check. I want you to check this and get the answer done. Now, so for all physical purposes, so we'll define a new thing from here. So this is our definition. Okay. So this function which you got, this is a very special function. This function, the function phi of r, it is always called phi of r, so sorry, it's called phi of x, so it is, see, this phi, this is like a universal symbol. Okay, whenever I write capital phi of r x like this, it is always fundamental solution. Yeah, in this kind of context, not in every context. I write it like this: 1 by minus 2 pi log of mod x. Okay, n equals to 2, and it is 1 by n minus 2 alpha n 1 by mod x to the power n minus 2 n greater than equal 3. Okay, so this is defined for x in Rn minus 0. Okay, and is called the fundamental solution of the Laplace equation, Clear? So this particular function which you get, see this function. So let us take some time and understand what is going on here. So I have got a u of x which looks like this, yeah, and what I am going to do is I am going to define a new function phi, yeah, capital Phi, yeah. So this capital Phi will look like, so I am taking b to be 0 and a to be minus 1 by 2 pi. There are reasons for doing this thing, yeah. So for now, let's just write it down, and we'll later you will see why we do all that. So minus 1 by 2 pi log of mod x, and this is 1 by n alpha n minus 2 alpha n mod 1 by mod x to the power n minus 2. So this is for n greater than 3. So for these two, you can always see this is also radial function, right? Yeah, this is also a radial function. Yeah, so this kind of thing is called a fundamental solution of the Laplace equation. Now you can see that as x tends to 0, yeah, as x is near 0, this blows up. This also at x equals to 0. I mean, of course, this does not blow up, but it is not defined at x equals to 0. Yeah, it is also not defined at x equals to 0. So essentially, if you just leave out the 0 part, this is defined everywhere, and it solves the Laplace equation everywhere except at 0. And we call this thing as a fundamental solution. Okay. So with this, we are going to end today's lecture.